G'day, my name's Daniel Dahl. I'm a PhD student at the University of Queensland, Australia, and I'll be presenting a device that is a high-dimensional Stokes-space Spatial beam analyzer. So what does this device do? Essentially, the device can take a beam that is an unknown spatial state and determine its amplitude, phase, and coherence in a single shot. Many of you are familiar with the characteristics of amplitude and phase of a beam. However, you might not be familiar with coherence. So what exactly do I mean by this? Coherence is referring to whether a spatial state is composed of multiple mutually incoherent fields. That is, fields with undefined phase between them. There are three types of coherence that a spatial state can have. Coherent, which could be a beam that has come from a single source, thus being composed of a single spatial state. Partially coherent, which would mean that the state is made up of a mixture of multiple fields of different powers that are not mutually coherent with one another. For example, two or more beams from a different source with different powers. And incoherent, which is similar to a partial coherent state, however the powers of each of the mutually incoherent fields are all equal. Please note that in these illustrations and throughout this presentation, the phase of a field is represented by its color and its amplitude by its brightness. Due to the ability of our device being able to measure amplitude, phase, and coherence in a single shot means that it can be used in a variety of applications, such as in mode division multiplexing, where beams from different sources would need to be characterized after passing through some common optical device, or determining the properties of a field after passing through or being emitted from a nonlinear system, like a doped fiber or VXL, which both cause mixing of fields. But the most obvious and I suppose most general role is as a single shot wavefront and coherence sensor, where, for example, some unknown spatial state of light that could be made up of a mixture of, say, n spatial fields can be measured and its phase, amplitude, and coherence can be determined. It is this use case that the rest of the presentation will be contextualized in. There are a few different methods for wavefront and coherence sensing, which all have their own merits and flaws. Some of the most common methods of wavefront sensing are those of homodyne and heterodyne detection, as shown here. These types of techniques work on the principle of interference, either by interfering the beam with itself, as in homodyne on the left, or using an external local oscillator, like in the case of heterodyne shown on the right. While these are relatively straightforward techniques, they both require some kind of reference beam and are only able to reconstruct the phase and amplitude of a beam and not its coherence. There are other techniques which can perform wavefront sensing that don't require a reference beam and are also capable of determining the coherence of a state. On the left is an illustration of a spatial field filter, where multiple sequential power measurements can be taken on an unknown mixed state. From these power measurements, the wavefront and field coherence of the beam can be determined. This type of technique, however, is lossy due to light having been scattered away during the spatial field filtering, and is slow due to the sequential nature of the measurement. Other techniques, like those illustrated on the right, can however perform wavefront and coherence sensing in a lossless and single-shot fashion. However, most of these methods require many optical components, are relatively complex, making them difficult to set up and maintain, and scale poorly for beams that contain a large number of mixed spatial fields. The device we are presenting here is relatively small and simple, being made up of only two major optical components, is theoretically lossless, and performs wavefront and coherence sensing in a single shot with no reference. To understand how our device can perform this measurement, it helps to understand how we would measure the polarization state of light. The reason for this is because the polarization state is a simpler two-dimensional or two-state system, which can then be generalized and expanded upon to explain the n-dimensional or n-state system, which our device is capable of measuring. To measure an unknown state of polarization, we would need to measure the power of each polarization component of the state. Those are the horizontal, vertical, anti-diagonal, diagonal, right circular, and left circular. This illustration shows how an unknown polarization state can be passed through polarizing beam splitters and/or a half or quarter wave plate to measure the power of each of the polarization components. This type of measurement results in a total of 6 power measurements, or 2n squared minus n measurements, where n is equal to 2. From these power measurements, the value of the Stokes vector of the polarization can be determined. We can then use the Stokes vectors to calculate the density matrix, which lets us see what mutually incoherent fields the polarization state is composed of. To construct the density matrix of an unknown polarization state, we sum the Pauli matrices, which are each weighted by their respective Stokes vector elements. And then, by performing an eigen decomposition on this density matrix, the unknown polarization state can be determined. In this example, we can see that the polarization state is made up of a mixture of 78% of one state and 22% of another. Great, we've determined how to measure the coherence of a two-state system. So how do we scale this up to multiple states? Well, essentially it's the same process, except you measure more power outputs and use Gell-Mann matrices, which are the generalized higher dimensional Pauli matrices, to obtain the required density matrix. So the basic principle of the high-dimensional Stokes device we are presenting is that it will take some unknown spatial state of light in that is made up of n spatial fields. Specifically for us, this will be 6. The device then outputs an array of 2n squared minus n spots, just like what was done for the polarization example. And then this spot array is analyzed in a similar fashion to the polarization example, but using the Gell-Mann matrices instead of the Pauli matrices to construct the density matrix, which is then used to determine the wavefront and coherence of the unknown spatial state. So in short, the unknown spatial state comes in, spot array comes out, spot array is analyzed, wavefront and coherence are determined. You're probably now wondering, how exactly do we separate the unknown spatial state into an array of spots? Well, we use a process called multiplane light conversion, or MPLC for short. An MPLC works by cascading light through a series of phase masks. The animation shown here illustrates how different orthogonal input fields bounce off a series of phase masks on an SLM and are each transformed into different orthogonal output fields. It's worth mentioning here that the output fields shown here are the corresponding ideal spot arrays that our high-dimensional Stokes device would output for the respective input fields. This illustration also shows a key characteristic of an MPLC, which is its ability to perform different spatial manipulations on different fields while keeping fixed phase masks. It is this characteristic that makes it uniquely capable of wavefront and coherence sensing in a single shot with theoretically no loss. Experimentally, an MPLC is a relatively compact optical device. These images are a top and side view of the generalized MPLC setup, where an input beam from a fiber is passed through the MPLC, which is outlined in a green square on the top view image on the left. The side view image on the right illustrates how the light is made to bounce off an SLM multiple times to allow the light to be transformed. For the high-dimensional Stokes device, the experimental setup is as follows. First, an MPLC is used to create a desired spatial field. This field is then imaged onto a camera and passed into a second MPLC. The second MPLC then manipulates the field into an array of spots, which is then analyzed, and the wavefront and coherence of the input state are determined. The setup shown here is capable of performing wavefront and coherence sensing on an unknown state that can be made up of a mixture of n equals 6 mutually incoherent fields. I'll now go through some preliminary results. The results we have taken are for 3 different sets of 6 pure or coherent spatial modes, where the sets are the first 6 Laguerre-Gaussian modes, the first 6 Hermite-Gaussian modes, and a set of 6 arbitrary orthogonal modes. All the measurements presented here were taken at a single wavelength of 1565 nanometers. We are still to test the full bandwidth of the experimental setup, however it has a theoretical bandwidth of plus or minus 40 nanometers. The first set of results is for the first 6 LG modes. As a reminder, the color represents the phase while the brightness represents the amplitude of the displayed fields. The top row shows the fields that were passed into the high-dimensional Stokes device. The middle row is the output spot array from the device, and the bottom row is the dominant eigenstate, which is the state with the largest normalized eigenvalue that results from the analysis of the spot arrays. The far right column of images shows the theoretical output of the experimental data if the pure state were considered as an incoherent mixture of fields. The top image shows what the incoherent beam would look like, essentially the total intensity of the input fields. The middle image shows the sum of the spot arrays, and the bottom image shows the density matrix that results from the sum of the Gell-Mann matrices as well as the trace of the square of the density matrix. In the ideal case, the trace would be 0.67 or a sixth. The field on the top and bottom are very similar with each other, only really having a slight global phase difference. This, along with the fact that the trace of the square density matrix is only 0.033 off the ideal value, indicates a good reconstruction of the field from the device. The next set of results is for the HG modes. The dominant eigenvalues, displayed on the bottom row of fields, seems to imply that the reconstruction is slightly worse than that of the LG modes, as they are all lower values. The dominant eigenstates themselves, however, look reasonably close to the desired input HG modes, and the trace of the square density matrix has decreased slightly, possibly implying a better reconstruction. At this point in time, we are still investigating the full capabilities of the device and believe that the quality of this reconstruction may be explained by the system being slightly out of focus or misaligned, and/or on the quality of the input HG modes themselves. It should be noted that the system was aligned for the LG results, and then without changing anything on the setup, the other two spatial orthogonal bases were measured. It's worth mentioning the difference between the geometry of the spot arrays for the individual HG and LG modes. Since the fields are spatially different, it is expected that the spot arrays will be different. The sum of all the spot arrays, which is shown on the right, would however be the same regardless of the input modes, as this is representing an incoherent state. And now for the final set of results, which are for an arbitrary set of 6 orthogonal modes. Compared with the previous two measurements, these measurements have much lower dominant eigenvalues, and the field reconstruction are much more dissimilar to the input fields. Again, we believe the reason why these results are not as good as the results from the LG modes is due to the same reasoning as previously mentioned for the HGs. In fact, if the system was out of focus and misaligned, we would expect that this set of measurements would be worse, as they are not free space propagating fields. While these results are not as good as the previous two, the fact that the sum of the individual spot arrays form the same hexagonal pattern as the LG and HG modes implies that the device is capable of handling arbitrary orthogonal mode sets. That's it, thanks for watching.